questions about last night's homework?
Read all the 35
Okay. Okay, good. Fair enough. All right. Well, so today's lesson is getting good at antiderivatives. And to illustrate the problem, consider this one. What is this guy? Somebody knows?
Inverse.
He says tangent, she says secant. Who's right? Oh no, we don't know. Inverse sine plus c. And this illustrates the problem. And that is that when you look at an antiderivative, you actually kind of just got to know your derivative rules hold so that you can recognize the derivatives when you see them. Yeah. Yes. So, the first step is to know your derivative rules. And I have a couple of tips. The first thing is that you should make for yourself a summary sheet of all of the derivative rules. How many of you have already done that as a part of studying for a previous test? Yeah, several of my class have, other classes have done that as well. So step 0 for tonight's homework is for you to make a summary sheet, a study sheet. For derivative rules. And the second thing is, having made that study sheet, then you want to practice it, quiz yourself a little bit every day. Frequent, short, self-quizzes. Okay, so you want to think of these frequent short self-quizzes as basically doing exercises. How many of you play a sport of some sort? Okay, and when you play a sport, every day before practice starts, you do some kind of stretching, some kind of calisthenics, right? And you do that because you basically want your muscles to be toned. In the same way, you want your derivative rules to be toned so that they are right on. Because you never know when a calculus teacher might pop out of the dark alley and ask you the antiderivative of 1 over root 1 minus x squared dx. The second thing is that we want to turn these derivative rules into antiderivative rules. And we're going to do some of that today. And it works like this. Since I know that the derivative of sine x is equal to cosine x, I can turn that into an antiderivative rule by saying that the antiderivative of cosine x is equal to sine x plus the mandatory constant c. Yes, it is. That's right. So the inverse sine is a really different function from the sine function. Because they are inverses, their derivatives would be reciprocals at opposite points. Imagine points. Okay. Let's do another one here. Let's see. Because I know that the derivative of e to the x is equal to e to the x, therefore, the antiderivative of e to the x dx is going to be equal to e to see how this goes. I'd like for you to do a couple for yourself. Go ahead and create two antiderivative rules for yourself based on derivative rules. Go.
Okay.
You have to make the rules.
Yes, based on the derivative rules. If you're working at home, you can also do that for yourself at this time. We'll come back. Okay, Tony, what's an antiderivative rule that you created?
Derivative of ln
So,
ln x.
I think you need to think in reverse. It would be the antiderivative of 1 over x.
Ln x.
And that's a good rule to know. There's a little bit of a domain problem here that we're going to address at the end of class. Notice that the domain of ln x is positives only, whereas the domain of 1 over x is all x but 0. And so we wonder exactly how that works out. We'll handle that at the end of class. Okay? Give me one that you have.
Derivative tangent, inverse tangent.
Is
1 plus x squared. 1 plus x squared.
there you go. Therefore,
So antiderivative 1 over 1 plus x squared equals to inverse tangent of x plus.
very good. Mark,
The derivative of tangent is secant squared. So then the antiderivative of secant squared x dx is tangent of x plus 2.
good. Go ahead.
Do you say the dx when you say it?
Yeah. Clara, do you have one?
Derivative of cosine x equal negative 5. So inverse antiderivative negative sin dx equals cosine x.
Very good. Jason, you got one?
Derivative of 1 over 5 times x to the x cube equals to 1 over x to the 1. So antiderivative of x to the 1 dx.
Good. Very good. That's very clever of you. Okay. So that's the spirit of these. Once you've got your derivative rules, then you're going to turn them into antiderivative rules. And Tony, you can see why, so that you get the logic nice clear in mind. Okay? Now, the third thing, and this will jump ahead a little bit, but I'm thinking 1, 2, 3. First, you're going to make yourself a derivative rule study sheet. You're going to study it a little bit every day. Frequent, short self-quizzes, by a little bit, 5 minutes. 5 minutes a day. And then you're going to turn the derivative rules into antiderivative rules. And then the third thing that you're going to do is be willing to use algebra. Well, let me generalize this actually. How about this? Develop a strategy for antiderivatives. Now, the reason I say a strategy is that taking derivatives, strategy. Taking derivatives is a matter of applying mechanical rules. If I give you any function that is composed of elementary functions, you're just going to apply the rules, and you're going to get the derivative, and there it is. Antiderivatives, not so much. Antiderivatives are puzzles to be solved. And so for that reason, you need a strategy. And our first element in our strategy is to simply recognize derivatives when you see them. And that's what all of this stuff in red is all about. We're recognizing derivatives and finding their antiderivatives. But then second, if we are confronted with something that is not obviously the derivative of something, we need to be willing to use algebra to rewrite it so that maybe it can become the derivative of some function. So, algebra is going to be our first line of defense after just immediate antiderivative. Now, let's see how all this works. I'd like to develop 4 antiderivative rules that will help us define antiderivatives of polynomials as well as other functions. Yes, ma'am?
So, it's set for the derivative that we can recognize. Can we deal with the inverse of the shortcut?
I may answer your question with what I'm about to do here. So, I would like to get a sum, difference, constant multiple rule, and power rule for antiderivatives. And if I have those 4 things, then I can find antiderivatives of any polynomial. Okay, so let's go. Because the derivative of a sum is the sum of derivatives, I can reverse this. Ooh, that was exciting. What are you doing? Oh, smartboard. Just move. There we go. Because the derivative of a sum is the sum of derivatives. Therefore, the antiderivative of a sum must also be the sum of antiderivatives. Now, students will sometimes get confused when they look at this. The f and the g right here are not the same as the f and the g right here. They are just any 2 functions, right? So the derivative of the sum of any 2 functions is the sum of the derivatives. Therefore, the antiderivative of the sum is equal to the sum of 2 antiderivatives. And the same applies to a difference. Because the derivative of a difference is the difference of derivatives, therefore, the antiderivative of a difference is the difference of antiderivatives. There it goes again. And because the derivative of a constant times f of x is equal to the constant times the derivative of f, therefore, if I run that rule in reverse, I get that the antiderivative of a constant times f is the same as the constant times the antiderivative of f. In other words, just as with derivatives, I can pull a constant multiple to the outside. Please do not forget the word constant. I get students that see the constant multiple rule and they get so excited about the constant multiple rule that they start pulling functions of x outside the interval. That will not work. And finally, the power rule. Let's examine the power rule for derivatives in detail. Recall that the power rule for derivatives is first multiply by the exponent and then subtract 1 from the exponent. So multiply by the exponent, then decrease exponent by 1. Well, if I want to run that rule in reverse, I need to reverse all of the steps in reverse order. So I need to first increase the exponent by 1, and then I need to divide by the new exponent. So that the antiderivative of x to the n is going to be x to the n plus 1 divided by n plus 1, of course plus c. Now let's just check this to make sure that it works out. First, constant multiple rule to bring the 1 over n plus 1 to the outside. And now use the power rule on this guy. 1 over n plus 1 times n plus 1, x to the n. Let's cancel. It all works. I should have. So we want to think of our power rule as add 1 to the power, divide by the new power. Let me do a quick example, and then I want to come back and examine a small defect in the power rule. So the quick example could be something like this. Suppose I want to pull off the antiderivative of x cubed plus 2x squared. Actually, I'm going to do it like I did in the other class in 6x squared. Okay. So looking at this, first I observe that I am taking the antiderivative of a sum. So I'm going to go term at a time and use the sum rule to break up my antiderivative integral. Next, I'm going to use the constant multiple rule, but here I'm going to be very clever. I know that 3x squared is exactly the antiderivative of x cubed. So if I leave 3x squared in my integram, then I can integrate that on the spot. But this is 2 times 3x squared, so I'm going to pull the constant 2 to the outside using the constant multiple rule, just like that. Did I have to do it this way? I didn't have to do it this way, but it was very clever for me to do it in this way. And now I can walk through term at a time. Here we can use the power rule, add 1 to the power, x to the 4th power, divide by the new power, over 4, plus. And this is exactly the derivative of x cubed, plus the mandatory constant c. Now what I could have done was to pull the entire 6 to the outside and use the power rule. And if I had done that, I would have, of course, gotten the same answer. Because I would have added 1 to the power, divided by the new power, and gotten 2x cubed plus c. So either way works, but I like where possible to have those exact derivatives right there. Okay, now I want to come back and examine a hiccup in the power rule. We've presented the power rule as add 1 to the power divided by the new power, but there is one exponent that could break the power rule. What one exponent would do it? -1, that's right. I would end up dividing by 0. Can't do that. So the power rule does not apply when n is -1. N can be other negative numbers, but not -1. So that's kind of weird and strange. And we wonder, what happens when x really is -1? Let's explore that a little bit. So we're talking about what is the antiderivative of x to the -1 power. But if I use a little bit of algebra to rewrite in a more familiar and friendly form, I see that x to the -1 is simply 1 over x. What is the function whose derivative is 1 over x? Yes! In the special case of n equals -1, I don't get a new power at all. I get a natural log. Yes?
So it's a n equals -1.
Be integers, fractions, whatever. That's right. So for example, going back to our power rule page right here, if I had the antiderivative of x to the -1/3, add 1 to the power,
So
divide by the new power. Dividing by 2/3 is the same as multiplying by 3/2. Let's see. So the only special exponent is exactly -1 right here. But we need to say a little bit more, because there is a domain problem here. And our domain problem is this. If I look at the graph of y equals ln x, it has a vertical asymptote at x equals 0, and it has a domain of x greater than 0. But if I look at the graph of its derivative, y equals 1 over x, then the function y equals 1 over x by itself, not considered as the derivative, but just considered as itself, has a domain that is larger than the function y equals ln x. So we wonder, what happens if I try to take the antiderivative of 1 over x for x's that are less than 0? Huh. Interesting. Well, clearly, I need to find, at least if possible, I need to be able to find a function whose derivative is 1 over x when x is less than 0. And I observe that this function is symmetric about the origin. So if this is the point x1 over x, then we have symmetry about the origin, like so. And so it occurs to me that if I were to take this graph of natural log x and simply reflect it about the line, about the y-axis, then I would get a function that has all the right slopes in all the right places. And to reflect this about the y-axis, I simply need to take the absolute value of the argument. So, the true general antiderivative of 1 over x is actually the natural log of the absolute value of x. Let's see. And the absolute value is necessary so that we have a proper derivative for both positive and negative x's. Let me prove to you that this really does work.
X cannot be 0.
That's right. The x cannot be 0. There is no function value when x is equal to 0, either for 1 over x or natural log x. If I I take the derivative of natural log x, I get natural log of the absolute value of x, I get 1 over the absolute value of x times the derivative of the absolute value of x. The absolute value, the derivative of the absolute value of x is the absolute value of x over x. And I get 1 over x. And the graph of the natural log of the absolute value of x looks like the graph of natural log reflected or mirrored about the y-axis, just like that. Does that make sense to everybody? So this is a special thing that you need to know. A special antiderivative rule for 1 over x. Okay, let's practice. First of all, let's consider a polynomial. Go ahead, find the antiderivative. When you're done, check yourself. Okay, Jennifer, what do you have?
X to the 6 over 6 minus 2x plus 2x cubed over 3 minus x plus c.
Did you check it? Good. Very good. Okay, let's consider this one. Ooh, this is interesting. What's interesting about it is there is somewhat of a temptation to just integrate the outside form, right? Add 1 to the 2, divide by that. If you try it, you'll find out that it doesn't exactly work. It's close, but it doesn't exactly work. Yes, that's exactly right. We're going to multiply this guy out and do some algebra first. And then come back and integrate. Now later on we'll have a slightly different way of dealing with this that will allow us to integrate the outside form directly, but we don't have that yet. And now let's see if we can do this term at a time. Mark, can you do this basically in your head?
Minus x squared over negative 6, but there's a negative 6 will come out, so then x squared is 2, so that's 36. Or plus x cubed over 2. So then the plus c.
Ah, very good. Gotcha.
And then you can simplify 6 and 6.
And I usually write the coefficients as fractions. Like that. Good. Okay. Let's try another. Okay, notice here that we have a quotient. And we did not do a quotient rule for antiderivatives. In fact, we will not do a quotient rule for antiderivatives. So this is not an elementary derivative. And woe betide you if you try to take the antiderivative of the top and the bottom and divide them. No. We'll get it wrong every time. Don't do that. Instead, let's consider, can I do some algebra first? And I can. I can rewrite this as 1 over x squared, or x to the minus 2 power, if you prefer, times x cubed minus 3x squared plus 2x minus 1. And now distributing, I get the antiderivative of x to the first minus 3x to the 0 plus 2x to the minus 1 minus x to the minus 2 dx. Before we go through and integrate, does the algebra make sense for everybody? And now we go through and integrate, term at a time. 1/2 x squared minus 3x plus special exponent alert minus 1. What is that going to give me? Natural log of the absolute value of x. Minus, add 1 to the power, x to the minus 1 power. Let's divide by the new power, divided by -1. No. We divide by the new power, not the old power. Yeah. And then I can clean this up a little bit. Like so. Now checking it looks fearsome, but it's not actually bad. The derivative of all this is equal to, walk through, term at a time. Like so. And then get yourself a common denominator. And we're good. Yes, sir.
We never use quotient rule for.
Correct. I have once in my life seen a book actually give a quotient rule for antiderivatives, and I've never seen it profitably used. Because it would have to be so contrived, right? You have to have a function that was just right. G f prime minus f g prime all over g squared is, the antiderivative of that is f over g. Well, okay. But how often does that come up? Not often. Yeah.
And for products, we just have to distribute.
For products at this point, yeah, you distribute. Because to use a product rule, you have to have something that goes in the form of fg prime, the antiderivative of fg prime plus g f prime. And we don't. Now, sneak peek to the end of the year. After we're all done with the AP exam. As part of Calc 2 material, I'll teach you a version of product rule that is frequently used. But as far as we're concerned at this time, no. Let's do one more. Okay, this looks pretty awful. So I say to myself, is this the basic antiderivative? Is this somebody's derivative that I know? No, it's not. So, can I rewrite it in some way using some algebra? Well, it does occur to me that a square root is the same as an exponent of 1/2. And I do have some exponent properties that can apply here. So that when I apply them, I now get a constant times the antiderivative of x to the 3/2. And hey, look, that's an exponent. Add 1 to the exponent. Divide by the new exponent. And we're done. So a little bit of algebra makes it all happen. And when I say algebra, I include also the trigonometric identities as part of that. So consider, for example, ooh, that looks really yucky. Until I go, huh, can I use trigonometric identities to rewrite 1 over cosine squared? Oh yes, 1 over cosine is secant, so 1 over cosine squared x is secant squared x. And now I recognize this. What is the function whose derivative is secant squared x? Tangent x, of course, plus c. Ta-da. So a little bit of algebra and trigonometric identities make it happen. And this can happen with really complex stuff. Look at this guy. That looks horrible, doesn't it? But wait a second. How can I rewrite 1 minus sine squared x more simply? Ah! And at least in the first quadrant, what is the square root of cosine squared x? Yes, it's just cosine x. That's exactly right. And the function whose derivative is cosine x? Plus c. So be on the alert for opportunities to use your trig identities as well. Questions or comments? Okay, well, I will see you guys tomorrow.